Our safe harbor statement. Please remember this advisor webcast is intended for information purposes only. Any feature or functionality described for Oracle's products remains at the sole discretion of Oracle. Now, let's get started with our presentation. Roger, if you are ready, I will turn over webcast to you.
Ready?
And you can begin.
Can you hear me?
Yes, we can hear you.
Great. Thank you for the introduction, Jens. My name is Roger Snowden. Within Oracle support, we do have a very small team called Center of Expertise, which sometimes they call a Center of Excellence, but we deny that emphatically. We specialize really in diagnostics. That is, we specialize in a generalization, if you will, problem solving in diagnostics, including bug diagnostics. But we see performance as a very large subset of diagnostics in general, so therefore we also serve as performance specialists very often. And this particular presentation is intended to be not so much theoretical, but really pragmatic. A lot of questions come up with AWR, and the full title of this, I don't know what your screen says, but it's actually Introduction to Performance Analysis using AWR and ASH. I've made an AWR automatic workload repository presentation a number of times, and but I had never included ASH until recently, which stands for Active Session History. The two tools and technologies give us two different views of the same thing, of performance. And I've often thought, and I think many of us on our panel here agree, that the two tools work very well hand in hand, and so it made sense to include them. So I took what was originally a 1-hour presentation, and I added some more information. So, and I have really about 45 minutes to present it, and we're starting 9 minutes after the hour. So what that means is I have to talk really fast, and for that I beg your forgiveness. And I'm going to have to omit a fair amount of detail, but our focus is on a high-level view of a pragmatic approach, and so we don't need to go through all the details of both AWR and ASH today. However, if you download the presentation that comes with this, I think I don't know when it's available, but it will be available. It's done as a PDF file from the original PowerPoint, and there are notes pages. And I think there's an entire running commentary. It's basically an article on all of this. So you can always take the bits that I skip over, and you can refer to them and study more on your own. You're not going to learn everything about the two reports anyway from any one presentation. And I would strongly advise you to participate in our forums and our communities through our website to get more information and ask for the questions. So to carry on here, let me get my navigation straight here. There we go. We're going to be talking about some basic concepts of performance, essentially identifying bottlenecks. That's really what performance is about, as we'll talk in a moment here. We're going to learn to characterize our particular problems, because we do need a good description of the suspect, so to speak. And then we'll identify problem sessions. The vast majority of the time you're dealing with performance issues, it comes down to usually a bad session, usually some sort of bad SQL. And the trick is really to identify it and then figure out what you're going to be doing to tune it or alleviate the problem. So we're going to go through that today. So we'll cover skim very quickly over some basic concepts that we'll be referring to. We'll talk a little bit about the interval sampling and the two different approaches that we use here. Then the AWR and then ASH, we're going to use a bit of a case study I picked up some months ago from some colleagues in South America that happened to use both AWR and ASH to analyze the exact same problem. So it's really a nice case to work with. Even though it's a very weird exception, it gives us a lot of opportunity to see how exceptions present themselves and how to identify a bottleneck and a session. So we'll do that. And then we're going to drive down toward a solution. As I said, typically you're going to be looking for a bad SQL statement of some sort, so we need to identify that, and this will help us do that. And then we'll talk a little bit also in the middle of this about the limitations of both AWR and ASH. So basically our methodology is this. We have something called the Oracle Diagnostic Method, which is a fairly comprehensive, really scientific methodology. It's based on the scientific method for problem solving in general. It involves lots of steps, details of testing and documentation. But when I look at performance, I really try to strip it down to its essence, because when you're approaching a performance problem, this is really what you're doing. Since a system is no faster than its worst bottleneck, what you're really doing is you're trying to find the worst bottleneck and then just relieve it. It's that simple. However, sometimes it's like peeling an onion. You take the outer layer and then you're presented with a new layer. Your entire performance issue may not have gone away. So what you have to do is keep repeating until you get back to some measure of what you call good performance. And so obviously with respect to that, it's good to have some reference point to know what we mean by good performance. There are no absolute numbers. It depends on what you and your users thought was good performance. So if things suddenly go awry on a Tuesday morning, if you know what was normal at some point, then you know when to quit tuning when you get back to that point. So it's really just that simple. So how do we find the worst bottleneck? Well, we need to get the information. And as we're getting information, both AWR and ASH are interval sample tools. That is, they take the instance and they grab information at intervals, and then we try to get some comparison of information from one point to the other and try to get it around the problem period. And the two take a different approach. So in AWR, by default, the interval sample is 30 minutes, although you can modify it, and I think in our case it was modified to 60 minutes, which is fine. What's important about this is that when you get an interval sample, that we get information closest to when during the problem period itself. So if you have a problem that presents itself at 10 o'clock on a Tuesday morning, it's no good to get information from 4 o'clock on a Monday afternoon when the problem isn't present. You have to have data from the period. And rather than getting a full 24-hour period, you want it to be around closest to around the problem period as possible, because otherwise the information we sample gets averaged out, and therefore the problem doesn't stand out like it should. Think of it as sort of zooming in with a camera. ASH is a little bit different, and then it gets 1-second intervals, and then later as we store this information to disk, it's stored at 10-second intervals. So we're throwing away 90% of our samples, but 10 seconds is phenomenally more resolute than the 30 minutes by default we get with AWR. So ASH is a very up-close and personal kind of tool, plus it's sampling data a little bit differently, which we'll discuss. So that's interval sampling. The response model, this is an important concept. We talk about response time. What do we mean by that? What we mean by, from the viewpoint of the user, is the combination of CPU time, that is time spent doing work in the database, plus time waiting for something, like a resource, like waiting for an I/O to respond, or some lock concurrency structure so we can access a piece of memory. So all of our sessions are either working or waiting all the time when they're busy in the database, and that gives us a response time. And this response model works at the enterprise level as well as at the session level. So if we look at something like, and in queuing time, by the way, when we look at queuing theory and discuss that, they'll use the term service time. You recognize that service time. When we talk in database terms, we use the word CPU time. It means the same thing as when we're actually doing work as opposed to waiting for an opportunity to do work. Now on DB time, I want to explain this. After having explained the response model, we can see here that in what I've got a sort of a naive diagram of an enterprise architecture. We see on the right side, let's say we have different browser sessions from workstations or PCs or whatever they are, and connected through a network to some middleware, some series of servers or one server, which in turn has sessions with a database over here on the right side. So response time from the viewpoint of the user is the time from the browser through the network to the middleware, time spent doing work and waiting inside the middleware, through the network once again, and through however many switches we go through to the database, then through the database working and waiting, and then sending the information back out the other way. So that's the overall response time. However, from the database, we only see what happens in the database. So we have a concept we call DB time, which is for all of those connected sessions, foreground sessions, how much time is spent in the database, not waiting for a message from the middleware, but waiting or trying to get work done, either consuming CPU or waiting for a resource internally. And any time that we're not doing that, we're what we call having what we call an idle wait, which would be typically SQLnet message from client, waiting for basically for the middleware to send us a message, a request. It's like waiting around the phone, waiting for work to do, and nobody's calling you, so we're idle, we're waiting. But when we have an assignment, when we have a SQL statement to process and rows to fetch, then we're working, and so we consider that DB time. And so if we had a problem with performance, and the real bottleneck was over here at the browser, or it was here in the Fusion middleware, something like that, but not in the database, then our DB consumption, our database time for that session would be reduced as opposed to increased. But if the database was the bottleneck of that response time, we would then expect the database to be a larger proportion of it. So this is kind of important to understand that concept, and we'll revisit this. So of the time we spend working, then we have CPUs burning, okay, and they're actually doing work. So if we look at the wall clock time, that is the time-space continuum flying by, and consider from this moment to that moment what happens, if we have 8 CPUs in our host, in our server, then we have 8 CPU seconds per second available as a resource. If we only have 1 CPU, then in 1 wall clock second, we can at most get 1 CPU a second to be able to execute. We never actually hit that number. But if we multiply times the number of CPUs, then our capacity in the server is the number of seconds in the interval times the number of actual physical CPU hardware, the machines that we have that are CPUs. So we have this concept of CPU seconds per second, which we see in the ASH report, which we'll see in a moment. So, and also to tidy this up, our case study that we're using, we're not going to see all of it. We don't get the really final result, so we don't get quite that satisfaction, but it's used as an example here for us. So it's a case where they have a single instance, not rack. They have an intermittent performance issue where they have a spike in library cache load lock waits, and then also some related library cache and row cache events shown in an AWR report. They gathered a 1-hour AWR report, or they generated a report from the samples around that 1-hour period. Plus, fortunately, they got 4 15-minute ASH reports during the exact same period. So we get 2 different views of the same problem, which is, to me, magnificent. It's something we don't see often enough. But it gives us a nice way of comparing and contrasting the 2 issues. And in our case, just for the purpose of satisfaction, it turned out to be an application bug, and we'll maybe theorize about why that is if we have time. But we don't really get the actual bug. But it was the application misbehaving for some reason. It's a little bit unusual, but it does happen. So let's take a look at an AWR report. And by the way, all this information has been obscured, so there's nothing identifying in it. So it's just nonsense strings I've put together, except for things like the platform that it's an HPUX machine. So across the top, we see the usual information with the time the instance started up. We see it's 11.202. It's not rack. And then we show in the hardware, we know it's HPUX. We see 16 CPUs, 8 cores, and 2 sockets. So what does that mean? When we think in terms of CPU capacity, we think numbers of CPUs. However, by CPU, we're talking about the physical, inside the chip itself, the actual CPU construct in there, the hardware itself, which is a core. So core count is what we really use for CPU count. Up here, the CPU count refers to symmetric multi-threading, which is the generic term for what in Intel, for example, is called hyper-threading. That's a feature they have that allows multiple threads to share CPUs and opportunistically execute CPU instructions while one particular process is waiting. The CPU is waiting for typically a far memory call that takes more than one machine cycle. So you don't really get 16 CPUs worth of capacity from a multi-threading type architecture. What you really get is 8 CPUs on an 8-core machine. So we're going to use cores as to mean CPUs. And if we see down below, we have the elapsed time. That's our 1 hour, more or less. And we see the DB time is 3,856 minutes. And if we look at the sessions, you see they're around 1,000 sessions. So what that means, if we divide by 1,000, we have about 38 minutes of, or is it 3.8 minutes? I guess 3.8 minutes of DB time spent per wall clock time in the instance. So we divide that down, you can get an idea of what it is per second. And then we look at our load profile. So I'm just going to skip over much of this stuff, but just show you the highlights, just the juicy bits, and then try to relate it to our case. Here we show DB time in a second. This is the seconds per second. So if we have 63 seconds per second, how many CPUs do we have? 8. So in a 1 hour period, we have 8 seconds per second available to us. we have 63 seconds of DB time, but CPU time, excuse me, I think I misspoke, is 1.8 seconds. Less than 2 CPUs are active per second. So that means we have less than 25% of busyness. And when we look at the operating system statistics in here, we should expect that to be below 3/4, right? So it's going to be around 20% busy or 25% busy, a little bit less than that, which means the rest of the time is idle. So that gives you a sense of workload versus capacity. But you see our DB time is considerably higher. Why? Because sessions are waiting for CPU. They're busy waiting, okay, if that makes sense to you. The opportunities to wait are limitless. The CPU capacity is finite. That's the point of all this. And then we see hard parses versus hard parses. I look at that only to, noted this only to indicate that what we call soft parses are really a derived number from parses minus hard parses. Hard parses are when we're constructing or reconstructing a cursor. Parse means looking up a cursor in the library cache and executing it. Of those, some of those result in hard parses. We prefer fewer hard parses, obviously, but that's what those numbers mean. And then we look down here. I'm going to skip over much of this except to mention that execute to parse means for every time we implement a cursor, we identify a cursor and execute it, we would prefer to parse it one time and execute it many times. So our execute to parse ratio, we would hope to be as high as possible. 71% doesn't strike me as terribly high, but it's reasonable. And then of the time spent actually doing parsing, 3% was actually CPU consumption versus waiting for resources such as shared memory and that sort of thing. So now we start getting to the heart of the thing. We show the top 5 timed events in the StatsPack predecessor to AWR. We always showed the top 5 wait events. Now we call it top 5 timed events because we include that foreground CPU time. And what does that do for us? It gives us the response model from which we derive the DB time. And so that's why DB time is important, because we're looking at a more realistic view of time actually spent in the database, what we're doing. And very often you will see CPU consumption as one of the top 5 events. In this case, it isn't. We see this weird thing, library cache load lock. And look at the average time here. It shows that it's 17,000 milliseconds. That means an average of 17 seconds average per acquisition of that library cache load lock, which in my mind is an extraordinary number. And it consumes about 17% of our DB time. So 17 seconds per execution is a huge number for something that is involved in a parse. Okay? So when we look at the events here, at some point you have to recognize what does each event mean. And so a library cache load lock, by analogy, if we're reading data from the buffer cache and we encounter a buffer, we say, okay, our buffer belongs here, but it's not there. Then our session has to read a block from disk because we didn't find our buffer in the buffer cache. As we're doing so, we create a new buffer. We assign one. And while we're reading it, we put a flag up. We call that a lock. And when other sessions try to read that, they find the same block. They say, oh, it's here, but it's not ready yet. We get this message that says, what do we call it? We say it's read by other session. It's part of the buffer busy wait. What that means is we're waiting for the foreground session to load that into the buffer cache. So by analogy, in the library cache load lock, when we're trying to parse a cursor, say select Roger from Dual, and we don't find it, our session has to construct it. So we create a library cache object. We flag it as being busy. We say we have this thing called the library cache load lock. Then when some other session, while we're constructing that cursor, comes along and tries to execute it, it sees library cache load lock. That means I'm waiting for that cursor to be constructed. So it's like read by other session, but it's building a cursor by other session. That's what that means. So 17 seconds is a very long time for that to be taking place, and we know it's related to parsing. But when you see these wait events, in order to understand what they mean, you really need to do a little bit of research, and that's where product knowledge comes into play. There's no real substitute for it, but you can get that information from our performance documents and My Oracle Support. You can also participate in the communities. And there's some very good documentation out there and a lot of expertise out there waiting to answer your question. So once you understand what something means, it's a little bit easier then to visualize what could possibly be causing this. So the next wait event down is cursor pen S wait on X. That's also a parse-related event. Cursor, it gives you a clue. Row cache lock and the next one, latch row cache object, are dictionary weight events, and typically involved also in parsing. And then finally, the library cache mutex, which in previous releases was always library cache latch, but now we say it's mutex. It's a different construct, but the same event is going on. That is the same. It's a hash table access that we're doing when we do a parse. So you can see all of the top events are parse related. That's very interesting to me. And I see the top event is this library cache load lock. Now, I might be tempted to go and deal with this library cache mutex X because I say, well, that's a slightly more familiar thing. I know how to tune it. There's no point tuning it if it's relatively small in the amount of wait time, because remember, our objective is to look for the worst bottleneck and relieve it. And our worst bottleneck in this case is overwhelmingly library cache load lock. So I can also tell you from experience that if you deal with the worst bottleneck, especially when wait events are related to the same phenomenon, in this case parsing, then when you relieve that top bottleneck and find out what was going wrong, there's a good chance the rest will go away, or they become so lessened that they're not the worst bottleneck anymore. So we always deal with the top bottleneck first. And then as we look further down, here's a little bit of performance information we get from the operating system, or it indirectly comes from the operating system. It shows our load average. We see our idle time of almost 80%, which comports with our view of CPU seconds per second. Recall that was 1.8 per second. That's the time busy. The inverse of that is the idle time, which is up around 80%. So that makes sense. So now we've got two different pieces of information that suggest that we're not CPU bound. So that's a good thing. Now we're into the time model statistics, and you will see this in the AWR report. This view that shows you different types of events, or categories of events, as a percentage of DB time do not add up to 100% normally. Why? Because, for example, in this case, SQL execute elapsed time, which is very typically the top time model event. That's everything involved in getting work done, parsing and retrieving, not parsing, but executing and getting information from cursors. That's the work we want done. So we expect that to be consuming the most resources. But also part of that includes burning CPU. So therefore, some of this DB CPU is included in the SQL to execute elapsed time. So therefore, this thing doesn't add to 100%. So that's a common question then, and so now you know the answer to it. And look at the bottom, we see DB time toward the bottom, and that, of course, doesn't show a percentage of DB time because that is DB time. That is our total DB time. And then we also show the background elapsed in CPU time. They don't get included. Remember, DB time is only for foreground sessions, so we disregard the background sessions for this. Okay, so it's now half past the hour, so I have 15 more minutes. So I'm going to speak even faster now and skip a lot of stuff. Operating statistics, review this. It conforms with what we've already observed. This comes from the operating system. If you're using a tool like OS Watcher, you can also use that directly to measure the operating system statistics. And if you're not using OS Watcher, I highly recommend you install and use it. It's very important. Get it from, I think in our notes at the end we show this. Now we show all of the foreground wait events, and it's really a recap. They also show timeouts, but that's not important in our case. Same information as the top 5. We just show them here, ordered by total wait time, not by number of waits or number of accesses or anything like that. We disregard that. We're concerned with our foreground time, so total wait time is important. And then average time is important because what we don't know, and this is what we're going to look at next, we don't know if this 17 seconds of average time is really spread evenly across all sessions, or is it just a handful of sessions that are causing this, and maybe most of the sessions are operating fine. You might know by talking to your users to know if only a handful of sessions are affected, or users are affected, but you can look at this and try to determine. So next up, we have this histogram, and it shows a breakdown by range of time for all of our events, and I've sliced out the particular events here so we can see our library cache load lock event. We show the number of waits, and then the buckets of under a millisecond, 2 milliseconds, 4, and we see these values doubling, so this is an exponential increasing table. And then finally, those greater than 1 second. So we see that 5% and 6.7% are all operating fairly quickly, but we do see that 37% of the waits are greater than 1 second, so that's kind of interesting. So we have this skewed distribution. And if we look further, we now, in the next following sections, I've sliced out here and put them together so we can see other ranges of histogram. 32 milliseconds, then eighth of a second, a quarter, and so forth, and those greater than 2 seconds, and then we go from the range of 2 seconds all the way up to 2 minutes, and then beyond that. So we can still see that greater than 2 seconds, we still have 37.4% are greater than 2 seconds of those weights. And then finally, in the range here, we show that under 2 seconds, most of them fall under 2 seconds, but still quite a few fall outside that range, and then we have some further. So I took the liberty of producing a graph from this. You don't need to do this yourself, but this just shows the skewing of the data. If we show the histogram buckets here with numbers of weights, we can see that they fall off toward the end. But now if we look at the wait time itself, okay, and again, we still have the doubling of the buckets. I show the average here of about 17 seconds in the green arrow that you see. But look at this group over here that have extremely high values. What this means is that we have a relatively small, a very small set of sessions with such extreme wait times that it pulls the average up high. And that's all I want to illustrate here, that if you look at the histogram values, you don't need to go through this much detail, but you can get a sense of how the event is distributed, okay, and you can learn something about what's going on here. Now in the next section, because we know what our top weight event is, we'd like to know how it impacts our performance, so we can find the offending session. The limit of AWR is that it shows you, it does a really good job of showing all the different SQL statements ordered by elapsed time and CPU and I/O and gets and reads, everything you see here. However, our particular event is involved in parsing, not execution. So our event isn't going to show up here. Nevertheless, if you're doing normal conventional tuning, you're going to see this. You're going to see, and you're going to go to, I'm going to back up again and mention one more thing. You would look at elapsed time to see which SQL has the most elapsed time, but depending upon your particular wait event, if it was, say, DB file sequential read and I/O event, you would skip CPU time. You might go straight to user I/O wait time and look at the top SQL there, and you would expect your worst SQL to be both in elapsed time and I/O wait time, the same SQL IDs in each, on gets and reads and so forth as well. But if you had DB CPU as a high wait event or high timed event, then you would expect elapsed time and CPU time to contain the offending SQL as a top SQL statement. So that's the key there. And if you read the notes that I included in this document, it should clarify that for you. And then from here, you simply look at it. Here we've ordered by elapsed time. We would see our SQL statement. You see the SQL ID. If you click on this in the AWR report, that's in HTML format, it'll go straight to the SQL body. You can see it. But you see the time contribution and the percent of CPU of each. This is taken from a different report because our particular report didn't have any interesting SQL in it. Because why? Because our problem's a parse problem, not an execution problem. But I wanted to illustrate this to you. You have the SQL ID here. That tells you right now, if this was your top SQL, you would get that SQL ID and you'd want to trace it or get information out of the instance to find out what the plan looks like and identify the SQL itself, and you're ready to start tuning. You're ready to start analyzing it, figuring it out. Same thing for order by CPU time. You get the same information, right? So, but it's more or less the same information, but it's ordered by time consumed and so forth. And you might consider the time consumed for that wait event times the number of executions. You might have one particular SQL that only has 1 or 2 executions, but a huge amount of time. But some then have a lot of accumulated time because they're executed so frequently. So that still has a huge impact. This case, it's one that's executed 35,000 times that has the relatively highest impact on CPU time. So it's still a candidate for tuning. Okay, and then I/O wait time and so forth. And we're going to skip through this in the interest of time so we can talk about the AWR report. Tons of other activity. You also see tablespace I/O stats. Bear in mind, when we look at that response model, when Oracle makes an I/O call, we get information back from the operating system. Actually, we measure elapsed time from the time we issue an I/O request to the time we get the information back. That is our average read time. What it doesn't tell you is what happened at the device level. At the device level, you also have the response model of service time, where you've got the head moving and getting data and cylinder spinning and so forth, versus queuing, time waiting for the request, because you might have a very congested device and the controller is very busy with a lot of requests queued up. So we just see the overall average read time. So in order to get detail on a problem, with I.O., you need to get information from the device level, from something like IO-stat or the equivalent, to try to characterize what device is having a problem and it's either congested or perhaps the device itself is failing. It could have a very high service time or read time. So buffer weight statistics, we're going to dispense with that now. Same with segment stats. Dictionary stats, very often when you see those dictionary events, sometimes they're involved in sequences, okay, because we're not caching sequences enough. And when you're looking at dictionary stats and you have a problem with a weight event, go to this section here and look at the modification request, because all modifications to a dictionary object, this is the data dictionary, have to be synchronized real time, or at least in event order. They have to be synchronized to disk, therefore they can incur more wait time because of I.O. writing it back to disk. In the case of sequences, the most common dictionary object to have problems, you can alleviate that by caching sequences, and sometimes that's appropriate. Very often it's appropriate for your database, but this is where you look as modification requests, and as opposed to reads and so forth. In the library cache, there are two things I really look at. I look here if I'm having a lot of hard parsing going on or reloads going on, I want to know about that. Reloads means we had a perfectly good SQL statement that is now, it has been flushed out or invalidated for some reason, and now has to be reloaded or reconstructed, which incurs basically a fresh hard parse. And that's kind of an evil thing. You don't want that to happen. That can happen if you don't have enough memory in the shared pool, for example, where we start flushing out memory. You're always going to have some reloads, but when they become problematic, this is what you're looking for. Same thing with invalidations. Invalidations means probably that you did some DDL, maybe analyze some objects during production hours, and you shouldn't have done that. Or if you're in an environment where you have a decision support like a data warehouse, a lot of times the power users, individual users, create their own subschema as a copy of a main table, and they do a bunch of SQL bang, bang, bang on the SQL execute, and then when they're through doing their shift, doing their work, they run the reports and they drop their schema. So you get invalidations there, but they don't mean a bad thing because they're only affecting their own now unused cursor. So look at those from the context of usage before you panic. So now, okay, now what do we have? Active session history. Okay, I mentioned before this is a much more rapid sample report, and what we have here for the same 1 hour period are 4 15-minute reports, and these blue lines represent really the sum of all of the foreground sessions that were active during that period. So you're really getting the session events going on, and we compile them together and get overall information, but we retain the details of each session. So that's a fantastic way of looking at it, because it's the best of real-time rapid sampling plus the broader interval sample itself, so we can find out what happened by session inside that 1 hour period. So it gives us another view, almost an orthogonal view or 90-degree angle view on the same information. Okay, same header information more or less. We see our instance at 11:02. We show our sample time. This is 15 minutes. We show average active sessions. That means sessions busy in the database on average during that period, and then average per CPU. So again, we see I think, I'm going to, maybe one of my colleagues on the panel will disagree, but I think this is probably misstated, because CPU count, I think, is also misstated here. It should be core count. So this really ought to be 0.30, I think, average active sessions per CPU. I could be wrong. It's not a high value in any regard in our case. But that has to do with that threading view and everything. So now we show our same top user events. Okay, but here we show something a little bit different, CPU plus wait for CPU. If CPU is presented in AWR, that's the actual CPU consumed statistically as reported by the operating system on those foreground sessions. However, in AWR, we take a slightly different view. We know what the elapsed time is for a CPU-intensive event such as a parse, and we know what wait times occurred in there because we break those out, waiting for a mutex or whatever. But what we don't know is of that elapsed time, it's reported as CPU time. We don't know how much was actual CPU burn or actually waiting for CPU. We could have been CPU bound during this period, and this would be included as CPU wait time, wait for CPU. But that's a slightly more esoteric event, and I invite you to read the notes for this and take away from that. In our case, it's not a big deal because we're not CPU bound. But we do show those events in the average sessions. And then we can look at our 4 different ASH reports. Here they are. 7 to 7:15, and then 7:15, 7:30, and so forth. If we look at our top events, we can look and we see some fairly innocuous stuff, the CPU and DB file sequential read at the first one. Average active sessions are pretty low. And then we see library cache lock shows up. That's interesting. But then all of a sudden in the third period, we see library cache load lock appear for the first time. We show our average active session jumps up to 38. It's very busy now. A lot of sessions waiting for this. Okay. And then other events that are also parse related, like we saw. And then finally in the fourth report, the library cache load lock, this is library cache lock, the library cache load lock disappears once again. So what that tells us is that of that 1 hour period, that the third 15-minute period contains really what the problem is. Okay, so it's a much narrower period than the 1 hour itself. And that event, the library cache load lock, the wait time was so profound that it drove the averages high enough to influence the 1 hour AWR report. So I find that interesting. Now we're going to come back to this in a moment. We get session details here. If we look at session details on any of these await events, you see the P1, P2, P3 parameters for the await event itself. Each wait event has a different set of parameters, what the parameters mean. In this case, it's object address. On an I/O event, it'll be something like file and block. This is not useful to us as users. This is useful to Oracle engineers who are doing deeper diagnostics, or maybe not at all. But for some events, it can be interesting because if I look back to a different period, I see DB file sequential read. I see the same values, but now it's file and block and block. So we can use another view and figure out what object was affected if we want to. Okay, so that's what that's useful for. And we also show SQL phases. And here we see during our regular reports, the parse phase was fairly innocuous and low. SQL execution was highest, as we would normally expect. Suddenly now in the 7:30 report, where a problem occurs, parse jumps up to be a very busy event. That again gives us another way of determining what our problem is. It informs us, yes, and in fact it is a parse event going on here. Okay, so we see two different views of the same thing to verify our suspicions. And now we show top SQL with events, and here's our bottom line right here. We show library cache load lock, that's our session. We didn't see it in the AWR report because it doesn't show the parse events, the parse SQL. Here we show the actual wait event with a SQL ID. That's our particular SQL. And if you look at row source, it's supposed to show you where in the plan we had a problem. Well, it's an insert statement, as you can see. There's no real plan involved, so that's not useful information. But if we were to take a conventional SQL ID and use this with another tool, say SQL T, which we won't talk about, but it's referenced in the notes, and there's a node ID for it to get information on it, we could then tune the SQL based upon the SQL ID and getting its plan and so forth. In this case, because it's a parse event, we have to think, why do we have this event? We'd probably file a service request with Oracle, and maybe they would file a bug, and it might come back to be. I would be suspicious. I would look at the application anyway and try to figure out where in the application this is occurring and try to look for an application bug, but Oracle then would advise you on that, okay, in that particular peculiar case. But in a conventional SQL, now we show also the top row sources, so that's another view of the same thing, okay, library cache, load lock, top events, and so forth. Skipping forward, because we're just about out of time, I'm going to get into our Q&A here. Some more interesting things. If you have a case where you're doing a lot of hard parsing and you don't think you're sharing SQL adequately, here we show top SQL using literals. Okay, so in a decision support environment, you'd expect to have a lot of these, but in an OLTP environment, you hope you're using bind variables. Here are the offenders, the sessions that are not using bind variables. So these find those for you, so they become candidates for tuning and modification. And then we also show if you're using the DBMS application info package to instrument your applications, so you can see I'm in the accounts payable and I'm in this particular update module or action or whatever it is. If you do that, this shows you where busy events were, and it gives you a way of tracing back to your application code. So that's very useful to have. Okay, and then we also show, as before, all the SQL text. Okay, so we find this stuff. We also find top blocking sessions. In many cases, this is absolutely essential. If you've got a lot of blocking going on, then we can always find a session that is being blocked. But it's very important to find out what the blocker is doing, and this shows you, at least for that particular sample period. So if we were able to get this information, say from a view real time, we could turn around and trace that session and maybe figure out what's going on in that session. This would give us a way of getting deeper diagnostics in cases where that becomes important. Not effective in our case because of this peculiarity of the event, but then we also show top latches. So top latches are magnificent. We show the sample intervals, a lot of detail here that happens to be affecting you. Now look at this. This last thing I want to show you is the distribution within the 15-minute report. So from this, we break it down into approximately 5-minute intervals, and there's like this little 3 of those and a little 23-second rump here. We can see within that 15-minute period that had our library cache load-like event, it goes from being the third event to the second event to the first event during that period. Okay, so we now see that it's even narrower than we thought. It happened in the middle of that 15, or toward the end of that 15-minute period, and then in the last bit it suddenly disappears. So it was a sudden onset problem, and it just as suddenly disappeared for us. So that could be of interest to get a sense of where we are. So that's a really quick blur, high-level view. As I said, please go back and read through the notes, see if you can recall what I said. I think this is being recorded, so you can always listen to my fast speech again and catch my mispronunciation. So what do you do now? For most conventional problems, you would then get the SQL ID in the session, and you would probably want to do a trace. You can use SQL T. It's a magnificent tool. It's really a set of tools created by a colleague, a former colleague, Carlos Sierra. And it allows you to extract test cases. It allows you to get detailed statistics on objects involved in a particular SQL. You can get this information out of the library cache or out of a trace file, however you like. And then you can use another great feature we have with 11G, which is SQL plan management, where if you have a plan that's behaving badly and say it's, want to modify the SQL, but you can't because it's third-party SQL, okay, you can take a test case of this, modify the plan at least syntactically, not semantically. You still want it to mean the same thing, but you can add hints and so forth to get a plan you like. Then take that SQL plan value and stuff it back into the server with SQL plan management, and SQL plan management will say, use this better plan no matter what is presented by the application. So that's a great way, and especially for upgrades where the optimizer might change, and you want to, for these few SQL statements, you prefer to use the original plan from the previous release. You can use SQL plan management to stabilize that. I think it's a great tool. So in our particular case, we found the top blocking session. We would probably want to get some trace on that anyway and look at it. We can find out what the blocking session is doing, and if we can't figure it out from here, we would go ahead and approach Oracle, file a service request in our unusual case, and we might look at the application code. And your Oracle engineer would probably say that, well, you might check the application code and then figure out what's going on. In this case, like a day or two after I got this case, the engineers came and said, yeah, we found there was a bug in the app, so that's all it was. And again, the only reason I use that example is because it was so profoundly a sore toe, a throbbing tooth. There's no doubt where the root canal needs to be done. It's this tooth, right? So that's really the presentation. I think we've got some, hope we have some questions queued up. So basically, to wrap up, everything should be analyzed in context. Compare good to bad. You still need that baseline or something good performance to compare to. Okay. You want the interval sample, as we've illustrated, to be as narrow as possible around the problem period. This particular customer is using 60-minute AWR report intervals. That's okay. I personally prefer the default 30 minutes. I think 5 minutes is way too narrow. So, stick with the default, but then use ASH as well, and then you get this up-close and personal foreground session event response, so you get a lot of detail within the same period, and look how quickly we're able to solve our problem, or at least identify the root of the problem. And then use the DB time model to sanity check what's going on. Is it the database or is it not? By the way, the DB time model implicitly exists in a SQL trace when you use TK-prof. You have the same information, including the overall session time, that includes the idle time, the wait time, as well as the information of what's going on inside a session to sanity check good performance versus bad performance using the DB time model. We'll do another class on that sometime. That's a fun topic in itself. Use the top events to try to drill down. That's identifying the worst bottleneck. The distribution of times helps you to understand and characterize the nature of the problem. I went into a lot of detail on that. You don't need to. You look at it from top view and say, aha, this is what's going on. And then typically, most often, you're going to be doing a SQL trace. How do you know what session? If AWR doesn't tell you, ASH will. And that is it. There are some reference notes. You can get those from the document. The SQL trace, we didn't talk about that much, but that's how you do it. There's a frequently asked questions on AWR and some great database information. SQL T, which used to be called, or formerly SQL T Explain, how to use it, as well as SQL Plan Management, and then frequently asked questions for that. Great documents to read. I recommend if you don't have somebody in your enterprise who is a SQL tuning expert, ask that person to download and begin using it and get used to SQL T. It's not a trivial tool. There's a little learning curve to it, but study it and know it and have it available to you, because it's good to have in a larger enterprise at least one person who specializes in this, who knows this tool very well and knows how to solve SQL problems, because you can do a lot of great things with respect to addressing performance issues.
Thanks to Roger and to all of you for joining us today. We hope you found this webcast valuable, and we look forward to having you joining us again. Please enjoy the remainder of your day.